So this is only now recording. So we've got those grouped out. So yes, Avogadro's number. Why did you place those things where you place them? That why isn't shown in your work. So if somebody was looking at this, they might ask, why did you choose to do it this way? This is where the talk through that we go through in class becomes important. So as long as you understand your own process of how you're organizing, which things happening where, you're okay as long as you end with the correct sequencing. So to that end, if we stop freaking moving the mouse, if we go through, the goal for this question was Sagan's of molecules. So if we track through, molecules of caffeine would cancel with, and it's unfortunately floating on the outside, the molecules of caffeine in our Sagan's conversion. Okay, so not visible, but it's way out there. The moles of caffeine cancels with the moles of caffeine from our periodic table. So we'll make that purple, I guess. Here, we can do it this way. There's a little red, a little green, little red, little purple. Okay, the green grams of caffeine that you have in the denominator there coming from your molar mass is going to cancel with the grams of caffeine from the given information in that particular question. And so those units end up canceling out, which would then leave you with just Sagan's of molecules. What makes this question kind of challenging is that nobody has seen Sagan's of molecules, and we have lots of powers of 10. So this really kind of pushes that process. Do you understand the process behind how and why we place the units, where we place them, and are you actually tracking the full proper unit? Because if you aren't tracking the full proper unit, you will lose track of where you've done your calculations, and you will end at the wrong spot. Okay? So this work is, as far as I'm concerned, spot on. It establishes where things are. If we read this right to left, okay, you started with the Sagan's for what you wanted in the numerator. Okay, I would argue the blue one doesn't make sense to bring in right away because nothing in that green conversion allows you to understand why you would use the blue conversion or why you would use that blue information. So to me personally, I would have started as step 1 green. I then would have moved to step 2 red. Once I had step 2 red, that's now going to introduce this concept of the moles of caffeine, which would then allow me to see, the purple conversion, and then it would allow me to see the blue conversion. Okay, that's where my logic would flow. Again, that logic is entirely up to you. Your work is fine. Okay, it's exactly the way it should be. So, good job on that. So, not that button. Too many buttons. Too many screens. And we'll just say, and this can officially be me because I'm supposed to be working today. So, that looks good. And for those people that may be coming in or out of this, it's kind of hard to tell who's here. This is everybody. So Chem 130 and OChem. Question B. Oh, does it get distorted on your end when I scroll through this? I don't have any objections to this logic of stepping this out. What I do see here is this is now very, very, first I do this, then I do this, then I do this, then I do this, then I do this, which means to me you're now running that many independent calculations. As long as you do the independent calculations correctly and string them together correctly, you're okay, and it's not a big deal. That can be challenging.
That's not mine.
I know. I was just scrolling through because I figured you've been putting up your pictures. And if we go through and look here, I did say this was okay. So if we go through, just in case you're wondering why I start jumping at the camera, I'm looking at a TV monitor that is about 20 feet away. Is this the same question? Oh, yeah, it is.
I think the only difference from this one and the other one is the fact that they just use H instead of H2.
Yeah. So this work is more correct, or is technically correct. The other one was technically not correct because they used the wrong formula. It has to be H2 because that's what's given in the equation. And so their answer comes out wrong because they don't have the proper formula usage. So this one is fully correct. Oh, son of a...
Was that you saying that the images are correct, but the written information above the images is incorrect?
So right now, what I'm saying is Victor's work. Oh, jeez. Victor's work showing up on page 7 is fully correct. All the way through. The work shown on page 6 has some simple mistakes because they have the molar mass wrong. As soon as they fix that, that's fine. The typed out explanation. So mass of hydrogen will lead me to find the mass of H2O. I'm going to object to that phrasing. Okay. It's not that it's wrong, but I feel it's misleading. Because what I'm seeing there is that is a one step. Conversion. And that is not true. Okay. As per all the work that's shown down underneath, that's not a one-step conversion. It's a true statement. You can do that, but again, it makes it sound like it's easier or shorter than it is, and it's not short. And if we move through the work, grams of hydrogen, I forget. Were we given grams of hydrogen? Yeah. This typed out work here looks good. Yeah, in fact, all of this is good.
That was the teacher's typing an explanation of that whole question. We spent some time on it, so I just want to make sure that what we were learning was correct.
Yeah, and it can be hard to... And the big issue that we're going to encounter is how do you get this information put into a typed document? And this is something that plagues chemistry all the way through. This is why we typically get a lot of online homework systems and why people struggle with the online homework, because the formatting is so critical to actually explaining how things work. How this is written out, this is valid The issue that I would have with it is that if we compare that work to, say, the work shown down here, the work here is shown in one step, one process. If we look at the typed out version, there's 2 equalities here, which means it's been broken into 2 steps. I don't think you should be solving things as multiple steps. You should be trying to string it together as one big problem. Okay, because because that's all it is. It is one question with multiple parts. If you can put all the parts together, put all the parts together. Don't say don't break each of those things down into those smaller sections. The parts up here, again, aren't wrong. They're, again, valid, but it's coming to, there's kind of an implication behind it. That's that the mass of hydrogen will lead me to find the mass of H2O. It does, but that makes it sound like it's one step, and it's not. And where this issue is going to come in is looking at it typed versus watching someone actually solve it and establish the work that's shown here. And so for all of these things, what you should be doing is looking at actual work written in. So when communicating with the subs, and Anthony, this is going to go to you and Victor, because I know you guys are with that sub, though I think you have a different sub next week. What they should do is they should walk through it as best they can. And then what you should be doing is, as they describe it to you, you should be writing that work down, take a picture of it, upload the picture. Okay. I've got a little bit more flexibility with the iPad, and I can draw that work in as I go through and discuss it, which allows us to make sure that everybody's on the same page with how we would establish and do that solve. The problem with typing it is that the formatting behind that is a challenge. It can be done, as you're now proving, but that takes more time. Okay. And it's that time commitment that just isn't as fluid as doing it by hand, if that makes sense. You're just trying to prove how fast you can do it. Good job. Good job.
No.
Show off.
What I'm saying is this the way, is what you're explaining the problem that we're running into?
Yes. That's the exact issue, is that you would have to go through and incorporate an equation editor, which some people are familiar with. A lot of students aren't, and it becomes a burden to try and show that. This is why when it comes to the show your work portion for both Chem 130 and OChem's going to have the exact same issue, if not worse. I want you to do it by hand and just upload the picture. That's going to be faster than you typing it in. If you feel that you can be faster typing those equations in, by all means, go ahead and do so. For OChem, there is another way you can do it. If we go to insert drawing, you can do a new drawing, which I'm not going to do because it's going to break my whole system right now. And you could use the mouse and draw in your structures or draw in the calculation work. It's more effort than is necessary. It's a lot easier just to blank piece of paper, write out your work, take a picture of it, upload the picture, and move on. It'll move much, much faster, and you'll be able to answer the questions and get more credit than dealing with the formatting stuff here. The formatting isn't bad. It's just not worth the effort, in my opinion. Does that make more sense, Anthony?
Yeah, no. I wanted to grasp what you were saying was the loss in translation.
Okay. Yep. And yeah, if I was forced to type it out quickly, this kind of work is what I would show. I don't like it. I don't think students can really pick up and learn from that, but that's what I would be forced to show. That's why I'm very thankful I have the tech.
Yeah, what was written and the way that, and it seems stupid because the H and the slash and the molar mass, that is what it is, but looking at it that way, it literally looks like trash on a page. I don't understand what I'm looking at.
Exactly.
It just, that whole explanation is completely lost on me.
Yeah, and if we
hoping there's a better way.
track with the work that's shown here, and I can't show it on my screen. I need to not be using my TV for this in the future. This grams of hydrogen is the grams of hydrogen down below. So it's possible that whoever wrote out this work was trying to follow this format of this written out. So that first time section, grams of hydrogen, is the 9 grams of hydrogen. There's your times, 1 mole of H, 1 mole of H, molar mass of H. There's the molar mass of H. So it is actually likely that this work was someone trying to write out what was written up there. And that's why they're making that mistake that H should actually be H2, not H. And that might be why they made that mistake down below. The work down here, I think, fixes the issue that I have with it, is that the typed stuff shows this as 2 calculations, and the work actually combined that into 1 calculation. So I think the work did a better job of the typing, but the work was probably a direct result of the typing based on what I'm seeing. And with that, I'm going to continue on because I'm pretty sure we beat that one to death pretty badly. This one I do have a walkthrough on for C. If Victor didn't...
Mike?
Oh, yes.
I have no idea why my D is not posting. But I think I'll have to cancel it and come on again. But can I just say the answers? Maybe we can see which you had it.
Yep, so we said the balancing was what, 2, 1, 2?
Yeah.
And then for A, what did you get?
For A, I'm going to go preserve oxygen and necessary to make 1 mole. Is it 3?
No. What you should end up with if you run that calculation is half a molecule of oxygen. And for B, you should get half a mole of oxygen.
Half a mole. So for the first one, it's going to be half a molecule of oxygen.
Yep.
Oh, yeah.
I can write that out really quickly. We want molecules of O2. It's sort of fitting on that screen. We were starting with molecule of nitrogen dioxide.
Yeah.
Molecule of nitrogen dioxide. Molecule of O2. Molecules of O2 is 1.
Okay, yeah, I see what I did wrong. Yeah.
Yeah. And so you would get half a molecule of O2. B is going to end up with the exact same thing, except in B, it now says moles. Come on. And then that's why when we get to C, it says, well, question A is invalid. The work that I wrote out was perfectly valid. So why is it invalid? But the answer for B is valid. So what do you think?
Does it have to do with the... I was thinking about 2 things. I was thinking, does it have to do with like the moles and molecules, or does it have to do with the fact that you cannot use a fraction for atoms or something like that?
It has to do with moles and molecules, and you're starting to potentially, when you say as a different thing, it's the same concept. You're not allowed to have half a molecule. Can you have half a mole? Well, what is a mole?
I think we can have half a mole.
A mole is a very large number of molecules. So if we keep it easy, just call it 10. Can I have half of 10 molecules? Yeah, I'm allowed half of 10 molecules. That's 5. I can't have half of an individual molecule because we can't split it in half and have a remaining piece floating around. We have to use the entire piece. So that's that discrepancy. This question is really asking kind of, are we allowed weird fractional answers with moles that we wouldn't be allowed with molecules? And yeah, we are, because mole is a really large number of them.
You said moles is a really large number of what?
I said them, just in general. It's molecules or atoms. A mole is just a really large number. So I can have I can have fractional moles. I can't have fractional things.
Yeah, because I was thinking like when you said atoms, right? Like having like half an atom is not possible because
Yes.
of the law of like you can't really destroy, right?
Yes. I wouldn't go with the law of conservation of mass or energy. I'd actually be pushing towards Dalton's rules, which technically are invalid, but we can't split an atom. The atom is the smallest workable piece. And workable becomes a bit of a weird phrase, but that's what I would use.
So yeah, I mean, yeah, I understand that, but because if you look at the question, it doesn't really say anything like an atom. That's why I was like thinking like if I like put it in terms of like atoms, like that concept, I don't know if it's actually valid for this question.
I wouldn't switch to atoms, but molecules are effectively the same thing. Once you have a molecule, it effectively becomes an atom. You're not allowed to split that up.
Yeah, sweet. Split and repost it.
So ABD, I think we're good there.
And I have a few of them multiple choice, which I could post to hit to be right now.
Please put it in the chat because it's the easiest place for me to do it. Right now, Branson's got a different one for me for OChem. So when I see the question in the chat, I'll try and work through them as I see them.
For sure.
Which means we're going to take a step out into OChem, which I'm sure all the OChem people appreciate. And I'm sure you guys appreciate because you always wanted to learn more chemistry too, didn't you? Oh, what did I just do? Not gonna worry about it. So we got a question for doing multiple choice 18, which is a fun one because we can't answer multiple choice 18 unless we also answer multiple choice 17. Because 18 is a direct reference of 17. Okay, so since, Branson, you decided that 18 is the question you've got, that means I'm going to have to then ask, what did you answer for 17?
I put C because there's two reagents to rate. Both in E2.
Yep. So when we go through and look at that rate law for, so I'm trying to get this figured out and trying to not type on that. Looking at that rate law, we have two molecules, which then means we need to be doing a bimolecular reaction, which means any of the two types. So we just look at our answer choices, and in our answer choices, that means A is wrong and D is wrong. Both B and C would be valid. We could try and nuance and try and decide between those. This would be that difference between nucleophile or base. If we looked at this one, if Robert's still there, what do you think? Is that negatively charged species going to be most likely as a base or a nucleophile? Base, good call, which means really we should just be saying E2, not SN2. I was trying to be a bit nice there and not make you nuance that difference and said that it was available for both SN2 and E2. Okay, so really Branson's answer was the best one. There's two things. It needs to be two type. C gets us the official answer, E2. The SN2 is kind of tossed in there as almost a side note, as a necessity to get the answer we want. Which then means we move to multiple choice 18. And it says, is odd. Why would it be odd? Well, that species, being very, very large, should only do an E2. which, dang it, did I really just give the answer? Yep, I did. Sweet. So I wasn't being nice by saying SN2 and D2. I was trying to set up question 18. Damn it. Way to ruin the surprise, Mike. The 2 was a valid way to answer that, which is what I was fishing for from Branson. And then the question that I was pushing and pushed towards Robert was trying to get you to recognize that that first molecule being so large would only act as a base, not as a nucleophile, which means the SN2 portion of your answer was a bad choice. It shouldn't be there. So for 18, the answer is it should only act as a base. Rates are bimolecular. That's why we have the 2s. So that answer is valid. Likely undergo only SN2. That would mean it was a small nucleophile. That's not small. I'll actually give you the name for it in a second, but that's definitely not small. So we could say maybe it would do an SN2, but it's a big freaking maybe. When we go to the last one, there's nothing odd about it. And yeah, there is. That structure or that negatively charged species is large and would likely act as a strong base, not as a nucleophile. The name of that compound is LDA. L stands for lithium because you're typically seeing to stabilize that negative, you need a positive metal to go with it. So you're typically seeing lithium associated with it. And then the D is for di because there's 2 groups here. Those groups are isopropyls. So it's lithium diisopropyl. And then amide, because you have that negative nitrogen. It might actually be, no, I think it's amide. So lithium L, di D, and then amide A. That species is typically known as LDA. It, in conjunction with T-butoxide, are your 2 really, really, really common bulky bases. So those are big ones to watch out for. Which I think means those questions are answered. And I don't see any more questions listed out, so.
Since you're close to it, can you 21 real quick?
Sure. Whoops.
No, I just want some writing. You gotta check out yourself.
Yeah, I think 21 actually has something on it. Because I think I did one of these page jobbers on it. Whoa. Oh, actually. Type of solvent. So, yeah, all of this red would be kind of my explanation behind it. Do you want me to walk through it again?
No, because I figured that because I saw that the CN changed to in the plane versus not like either dashed or wedged. So I figured that was like an inversion of stereochemistry. So with an SN2, that's usually a polar sulfate, right?
Pull back on that, unfortunately. If you were only given that equation, even if you were only given that equation, I would disagree with that analysis. You're starting with that wedge, which means that structure needs to be either wedged or dashed or shown as both. And the both is a squiggly line, which you will sometimes see. If you remember the models lab, that's a horrible squiggle, but I'm trying to show it. The models lab showed that with thalidomide. It's saying that it could either be wedged or dashed. Where you should be going is, yes, looking at the equation, but then also make sure that there's nothing relevant in the question to help you out. This says optically active product. So the question is now specifically stating that there is stereochemistry associated with that product. It's not being specified in the equation because if we specify that information, that adds more information to it where you don't have to have reading comprehension. So the question, by formatting it this way, necessitates some form of reading comprehension. So make sure you read the question. Because we know it's optically active, now I would say it's SN2. It really has very little to do with the equation itself telling you that it's SN2. Okay. Still not seeing questions from anybody. Oh, question on smart work is probably going to break my computer, but yes, we can try. And I just realized there's great information in there, so I got to hide that. Haley, since you asked, do you mind if people see how you did on whatever that question was? That you also need to tell me what it is? And are you okay with people seeing your progress on that question? You don't have to share. I'm getting your permission before I share it. I am not judging how far you've gotten. And I would assume most people aren't judging, even if they are. Tough, would be my opinion. They can take their judgment and shove it. I think you can quote me on that. That's recorded even. Fantastic. Well, on that note, let's hide the solution. Whoa, what are you doing? Never mind the man behind the curtain. SN2 or E2, and then draw your major product. So, which is good because this will go back to kind of Robert's questions on deciding SN2 versus E2. If we take a look at our first attempt in theory, no, don't show the solution. What are you doing? Okay, here we go. Draw the major product predicted for the following reaction. So what we're trying to decide is which reaction should we be doing, substitution or elimination. So in deciding that, where you should be referencing is I've got that kind of chart thing. Drawing this is going to be awful. I apologize. But remember I had that chart thing where we had the 4 SN1, SN2, E1, E2, and then substrate, nucleophile, heat. I don't remember all the things I had on it. Okay. What you should be doing is effectively moving through that chart to decide what information you're given and how that applies into this. Okay. We have some information already being applied for us. That information is that it's SN2 or E2, so we could ignore SN1 and we could ignore E1. And so really what we're trying to do is just differentiate between those two, SN2 versus E2. which route works best. In that process, we would start with our substrate. So in looking at our substrate, that would be this guy. We need to look for the site of reactivity. The reactivity is where our most electronegative element is. That's going to be our oxygen. We could either move to the T, being the reactive part, or we could move to the C, being the reactive part. Probably a good idea would be jumping straight to the carbon and not to the T, because T isn't a particular element. That's going to be something bizarre and weird. And if it's bizarre and weird, try to ignore it, because it's probably only there to confuse you. So focus at the carbon. That carbon is connected to 2 other carbons, which means we're looking at a secondary substrate. Okay? Since it is secondary, all reactions are favored. If all reactions can work, evaluating the substrate was utterly useless to deciding which mechanism we should run. Okay? So then we could move through to the next piece of information. We could look at our nucleophile or base. Okay? We are looking at this being strong, which was already kind of given to us because they said it was SN2 or E2. Strong means a 2-type mechanism. Okay, now what we really got to decide is between our SN2, it acting as a nucleophile, versus the E2, it acting as a base. Well, the nucleophiles, our halides, are going to be exclusive as nucleophiles and small. Okay. We'll call it ideally small to act as a nucleophile. For our bases, it doesn't have to be small, okay? But big is generally a big red or a red flag. That just looks awful. Let me try that again. We're going to write generally. Generally big. So if we go through and look at this substrate, we're looking at our nucleophile: oxygen, carbon, hydrogen, hydrogen, hydrogen. It's not the smallest it could possibly be, but that's pretty dang small. Okay? Because it is so small, that is most likely that we're going to be fitting in the nucleophile category, and we should be running a substitution, in particular an SN2 substitution. So that means if we're going to add curved arrows into this, that our nucleophile should come in and attack and kick out the leaving group. Since I have nowhere else to write it, I'm going to have to erase all of that work. And we now have OCH3. Before we get too excited about saying this is our final answer, we do have to be kind of critical of stereochemistry, particularly because stereochemistry is specified in the starting. Since it's specified, we should make sure that we look at it for our product. We're looking at an SN2. This is a backside attack, which means your nucleophile needs to come in from the backside of the leaving group. The leaving group is aimed away from you. Backside of away is towards, which means we should be wedged. Okay? So that would be a first guess pass at this. The question did say decide for the following reactions, plural, between SN2 and E2. So I'm going to take a stab that if I undo this drawing and scroll down carefully, that we have another problem in front of us. And indeed we do. So there's another system here. We might look at this and be like, well, nothing's changed. Okay, so that might set up alarm bells that maybe we shouldn't have drawn in that structure that we already drew. If nothing's changed, wouldn't we have the exact same answer? That seems a bit silly. Okay, so we could continue to scroll to see if there's something else. There isn't. So let's now be a little bit more critical about what we were looking at when we looked at our problem. So here's this reaction. Move to the top one. The structure and the nucleophile and or base are all the same, but the temperature has changed. This was 25 degrees Celsius. This is where having some familiarity with what those numbers mean in those units is helpful. 25 degrees Celsius is a roughly room temperature. which means we're running this reaction not hot. We go to the bottom one, we're now at 85 degrees Celsius. That is actually pretty hot. Okay? One of the red flags for an elimination is heat. Okay? And as you're drawing attention to, that we're doing a different temperature. So lower temperatures don't necessarily mean substitution. It's more the other way around. Higher temperatures typically mean elimination. Okay? And why? You're trying to break a carbon-hydrogen bond. Okay? That hydrogen is not particularly acidic. Why is it not particularly acidic? Carbon can't stabilize the electrons very well, which is why we need to use a strong base to do the elimination. And we need to add heat, and that heat is going to cause that bond to vibrate and effectively weaken. When that bond vibrates enough, the electrons can come out, eject our leaving group, and we would end with our final product with the pi bond there. So the assumptions that we went through and made with the first one were actually okay, though technically misguided, because we kept our focus on the nucleophile instead of looking at the temperature. When we see that temperature increase, this small nucleophile can now act as a base because we provided enough energy to help weaken the bond to allow the elimination to occur. So size isn't the only thing that helps us do our reactions. Temperature can make a really big effect on our overall reactions as well. Okay? I would also argue that they threw on those other pieces to confuse you. And by other pieces, I mean up here, because you might be like, well, I need the most substituted double bond. That would be a pentavalent carbon. Can't do that, which is why that one's wrong. Okay. They may also have it there because I think this is a grouped question, and the other grouping of questions is SN1 versus E1. And in that case, we're going to get a rearrangement. Strong, and so in your question, when you're saying strong base, I would argue get rid of base. Notice that what I've written is strong. Why is it strong? It's strong because of the negative charge. Absolutely not a guarantee. Okay, but that tends to be a good indicator that you're looking at something that is strong. Okay. So a negative oxygen would be strong, a negative chloride would be strong. The chloride will only be a strong nucleophile. The oxygen could be a nucleophile or a base. Why? Chlorides can't act as bases because then they would form strong acids. Okay? So, we got one of the questions from Smart Work done. Other questions? Sure, I don't see any other questions. Yep. Okay. Go away. 23 and 25. Oof. Recording. We identified the negative on that base or nucleophile. We could now have that potentially hook up and form a product, oxygen, where we're now connecting out where it acted as a nucleophile and we got the SN reaction. We could have also potentially had it react in the elimination type situation, whereas in the elimination, you're going to be removing the hydrogen and you'd end up with that structure. Everybody on the same page? Okay. Sorry, give me a sec. Reading Robert's question. Okay, I think I know where you're going with that, which works. So Robert is suggesting that what he saw here looks roughly like SO4 minus 2, as in H2SO4, a very strong acid. Why is H2SO4 a very strong acid? It can stabilize that negative charge very well. Okay, and why is it stabilizing the negative charge? The conjugate base, again, resonance. Okay, so it's still tying back to all those same things. So the answer or the description you're trying to give, Robert, I think is an argument that you've memorized it based off of past experience. That's fine. I'd like you to dig a little bit deeper so that you could get out to those pieces, because you may not see that always pop up. But yes, that's exactly why it's a good leaving group, is because it can stabilize, very similar to the strong acid. So back to the question, we've got the SN option, our substitution or our elimination. So now it would be a question of going through and seeing which of those answer choices match that, which means I'm now going to have to delete everything so that I can get back to it, at least so that I can see it. And we see that D is the only one that matches that result. Okay? And you'll notice that all the other answers have a variety of associations and pieces that could make them appear to be correct. This is why you really have to focus in on where that chemistry is located, identify it, and move forward. Yeah. So went through lots of stuff in the chat. I believe that was Sierra. Does that work for you for 23? Okay. And then we had 25, which is a very kind of similar situation, believe it or not. Keep pounding on the keyboard, and I keep forgetting. So when we go through and look at 25, we want to kind of walk through this again. We're given some information in the question that we're going through an SN1 reaction, which means we should be forming carbocations whenever we get an opportunity. Okay. If we go through and look at our reagents, we're given a strong acid. So we're going to want to neutralize the reactivity of the strong acid first. To neutralize that, we would need electrons. The electrons are found on our oxygen. So our very first step, I'm just going to write pH, which I'll have to undo in a little bit. Write a pH, put an H. That oxygen would be positively charged. Because this is SN1, I need to have our leaving group leave. So that oxygen would need to take electrons. So now the question becomes, damn it, I need to show the pH. Where should I take the electrons from? Should I take it from green side, or should I take it from the purple side?
Purple because of tertiary.
Purple because of tertiary, I'll accept that at least for the moment. So if we go through and follow that purple route, we'd have our OH with its electrons now neutral. We'd have the carbocation. What can that carbocation now potentially do? We've got the bromide still floating around. The Br- can react. And we would end with our OH and the bromide, and we'd have our answer. Okay? Could we have pulled it from the other side? When in doubt, it can be helpful to go ahead and draw it out. You'll be doing this lab next week in OChem. Which I probably should have moved it up, but oh well. That structure is a funny carbocation that is not technically a secondary carbocation because of where the electrons are located and everything else, and the hybridization. That is typically referred to as an sp2 carbocation, and what's special about sp2 carbocations is they cannot form. If they cannot form, that reaction does not actually occur, which means the green arrow never happens. Okay, so it's all about stability. Why does that become important to us? Okay, it'll become important because at the end of our reaction, we still have electrons on that oxygen. Those electrons could still react with more hydrogen. Okay, we could potentially go through and foresee a situation where we have this positive oxygen. Well, that positive oxygen doesn't want to be positive. Where does it get electrons from? And the tendency is that people will try and pull it from the ring. That would again form that carbocation, which means we can't pull it from the ring. We end up pulling it from one of the hydrogens, which means we actually go backwards. There's our final answer, which I can't tell if you could see, shows up on my screen, on one of my screens. It doesn't show up on the other. But that now is my final answer, and that's where I would have to end it. Where you have to be careful is particularly if you look at the ACS study guide, we can make a subtle change to the structure. What's the subtle change? No longer an aromatic ring. When it's no longer an aromatic ring, would I be able to form a secondary carbocation? Yes, which means the reaction could run again. Okay, and that's where when you go through and look at your answer choices, all of these possible combinations show up. So I believe the answer we ended with was A. B is it did it twice. Okay. C is it did the wrong path. And then D, sometimes there's just a random wrong answer. Okay. We do have those OHs there, so they kind of make sense, but we did nothing with the nucleophile, and we invented a new oxygen to go through and do that reaction. Okay. So I think that addresses your question again, Sierra. Deciding to Haley's question of deciding if something is SN1 or SN2. We sort of talked about it earlier, and I'm going to draw a horrible version of the table again. Okay, we're looking at that rough table that's in the slides somewhere. SN1, SN2, E1, E2, and then it lists out substrate, nucleophile, base, heat, and I think solvents on there. And so what you would have to go through and do to answer your question specifically is to evaluate what is your substrate. If it's a tertiary substrate, that's a check for the SN1, not good for the SN2. And so you can almost play it like tic-tac-toe. Whichever one has the most checks, that's the reaction you should be running. Okay, so you're trying to evaluate between those. If you're simplifying it to just SN1 and SN2, usually the big red flag that differentiates those is that the two type mechanisms require strong. So you would need to see a negative charge. So you see a negative charge, you're doing the two type mechanism. If you've now limited it to just substitution, strong nucleophile means SN2. Chase's question, with the extraction lab, is there a list of compounds that we use to decide what's in the mixture? Yes, there is. It should be in that background document. I believe it is benzoic acid, fluorinone, and I think this is it. Sorry. I think it's ethyl 4-aminobenzoate. It's 2. I think I had to adjust it because the melting points were too close. Oh, come on. So we got to wait for half an hour for the document to load. Let's try this. Well, actually, Branson said what it was, so it is there somewhere. Branson, do you remember where it is?
It's be just before the discussion conclusion part. Yeah, right there.
Oh, there they are. Yeah. So Chase, yeah, and the sub sent me some questions about this too. This is challenging. I will fully admit this, but you also aren't doing the lab, which is challenging also. So that's why I feel okay making it this kind of challenging. So you get to decide effectively what you were given. I'm giving you 200 milligrams of a mixture of these three things. Your results should mimic what you think that sample is. If you think it's a 1-to-1-to-1 mixture, what would that mean your percent yields would be? If you want to say 3/4 of it was fluorinone and then the rest was benzoic acid and methyl 2-aminobenzoate, then you can make those adjustments. One of the things that I would highly recommend that you consider within that is that, do you expect there to be a perfect yield? Would you expect to get all of the compound back when going through and running this extraction? As a hint, no. Okay, so you should decide how much you're going to lose. What do you think would be an accurate result? You've done a recrystallization. What was your percent recovery from the recrystallization? Use that to inform your decision for what your results should be as far as yield go. Melting points are things you should just be able to look up. So there's nothing particularly fancy there. But I think, after that, we do have the potential for IR and NMR, but I don't think the procedure suggested that you do those. Yeah, I don't see it there. Obtain a weight, melting point. Okay, so you are kind of creating what those results should be. If you wanted to throw in IR and NMR, you could do that, but the procedure didn't ask you to do that, so I can't expect you to do that. I might want you to, but I didn't ask it, so too late for me. Good luck for you.
Number 6 in the post-lab question, I'm just kind of stuck because I don't know if I'm just overthinking it, but it's benzoic acid and phenol. One's clearly an acid. Phenol is clearly a base. Acid and a base.
Phenol is not a base.
Okay.
pKa of phenol is about 10. Water that acts as both an acid and a base is at 16. So phenol is more acidic than water. So phenol is certainly not a base.
Okay, so that's why I was overthinking it, because I was thinking it would be acting as a base because of benzoic acids in there.
Yeah, nope. That's why the questions 1, 2, 3, 4 are kind of written up for you to go through and evaluate. And when you look at them, it's benzoic acid with sodium bicarbonate. Bicarbonate's usually a base. Sodium hydroxide, base. So acid with base. Phenol with the exact same substances being as bases. If you draw out those reactions, which is what you should be doing, that's what it actually asks you to do, and then put in your pKa information, you'll see that it should be acting as an acid. It should not be acting as a base. Because it's lab related, I'll jump to Robert's most recent question here. points being deducted is definitely going to be fun. Trying to figure that one out. If you rationalize it, really what you're trying to do is rationalize whatever result you get. So if you want to say you're getting a percent recovery over 100%, and you can rationalize why that's going to happen, and it's not an alien came down and gave you more, you're good. Okay, so you should be using science to rationalize the results that you get. And as long as your rationalization is there, yeah, I'll be giving you points for whatever those results are. One of the reasons why I've kind of created it open-ended this way is to kind of cut back on a lot of kind of the cheating aspects behind this. Now, if multiple people submit the exact same results, that's a pretty big red flag that someone was cheating, or copying the results of somebody else when you were explicitly told to not. So I do expect there will be some overlap, but that overlap should be relatively minimal and pretty obvious when there's direct copying of results. So you can talk with other people about what you think should be happening or where things would fall, or what kind of losses you would expect, but you should not be getting the exact same results as anybody else. And as long as you explain why you think those results make sense, that explanation is ultimately the biggest differentiator between individual students. So I'll be able to see there that you're doing things differently. And then I'm seeing a reference to a 26. Oof. Did I do that from the right person? Yes. Um, 26. So finding a reagent. So one of the biggest things that you should be trying to do when you look, because these are very typical kind of questions, is what is the reagent to do a reaction? And they can become very, very daunting because what people are doing is memorizing a reagent and then saying what, associating that with a particular reaction. But what people aren't doing is memorizing what reactions look like. So this is why in multiple cases you see those reaction summaries: acid, base, substitution, elimination, addition, and radical, that those reaction classes are written out for you both in text and in structures so that you get familiar and are able to recognize what a particular reaction type is. Once you know the reaction type, you can now kind of narrow the field on what your potential reagents are. So if you memorize reagents to reaction types as opposed to structures, that can help you answer questions like this. So in this particular situation, we are looking at running an elimination reaction because we see the formation of a pi bond. Okay, so to do an elimination, typically we would need a strong base. Oh, this is going to look weird. Oh, this is going to look way weird for the recording because we talked through a whole bunch of stuff and I had something else on the screen. Sorry. So we're running an elimination reaction. In eliminations, we're typically looking for heat, which isn't a reagent, so that doesn't help us out. And we're typically looking for bases because we're trying to break that bond. Usually we would see a strong base, but a strong base is really only necessary if we're doing an E2. Okay, so we got to be a little bit careful with saying it has to be strong. So base, how do we know we have a base? Negative charge, that's again tying to strong, okay, or electrons. So if we go through and look at our answer choices, of course, I can only see 3 on my computer. A comes in with a strong base, B is a strong acid, C is a strong acid, and now I'm going to have to delete all the work so I can see D. And D is a strong base. Okay, so we might immediately eliminate B and C because those don't provide us that strong base characteristic, and we could look at A and D. If we look, D is asterically hindered, okay, and this is where it is helpful to be familiar with converting your formulas into structures. We had that CCH33. I know it didn't officially say that, but close enough. Carbon, CH3. This is our T-butoxide. This is an exceptionally sterically hindered structure, which means this is going to act exclusively as a base, right? And so it's going to deprotonate. A, on the other hand, we're looking at one carbon connected to our carbon where the oxygen is. That's less sterically hindered. That could push a substitution. That could act as a nucleophile. Because I only want to do elimination, cool, base, the answer must be D, because that fits our category. But wait, there's more. We need to pause and kind of consider and evaluate what we're looking at and how we're approaching this. Whatever. So what do I mean? Bases deprotonate or remove hydrogens from acids. Which hydrogens do they remove? They remove the most acidic hydrogens. So if we go through and look at this, that red hydrogen isn't as likely to be removed as that blue hydrogen, because that blue hydrogen could remove and we could eject the leaving group, and we would thereby have our elimination product. So the red hydrogen isn't a good one because it can't stabilize that charge very well. Okay. Well, the other thing to consider is that in the formation of this reaction, this thing in red, now in purple, had to be occurring. And I picked purple as a color because in the videos we color-coded that purple as an LG, or as a leaving group. And if we look at this overall reaction, what we're suggesting is our leaving group is OH-. That should send up alarm bells because OH- is not a good leaving group. Okay? It should send up more alarm bells because the hydrogen connected to the oxygen is more acidic than the blue one, because oxygen can better stabilize that charge than the carbon, which means if I throw this strong base at that structure, what it's going to do is deprotonate, but it's going to deprotonate the oxygen, making a negative charge. Now my leaving group isn't OH-, it would actually be O-2, which should also make us go, oh crap, this is not going to work. Adding that strong base actually prevents this reaction from occurring, because the strong base is only going to deprotonate the oxygen, making a horrible leaving group, and now the reaction's not going to occur. This is the perfect question for people that memorize these reactions. So this is why we should test, pick what we want, draw out the result, and test that process out, and consider the reactivity of the entire molecule. Okay, so we've now completely eliminated all answer choices if we're paying attention to how we just walked through this, because B and C we said weren't bases, so we should get rid of them. A and D, now being strong bases, will deprotonate the oxygen, making a bad leaving group, which means I've now eliminated all answer choices. Take a deep breath. In our analysis, we said that leaving group needed to leave. Okay? OH- was a bad leaving group. How do I make it a good leaving group? What would make OH- more stable? Well, instead of being negative, it would need to be neutral. So I would need to attach something positive to it, kind of like a hydrogen. H2O would be a pretty good leaving group. But to get that H on there, I would have to supply that H. I would have to supply that H from, shnikes, an acid. The very first answers we eliminated are now our better choice, because the reaction forces us in that direction. Okay? Yay! So now which of these two would be the better reagent to do to supply that H+? Okay? Well, what do I want the reagent to do? Well, just supply H+. I'm only trying to turn the OH into a good leaving group. If I supply anything else that's reactive, that's only going to cancel the reactivity of the acid and potentially do other things. So if we go through and take a look at these, for answer choice, what is it, B? B, we would end up with that structure. For answer choice C, we would end up with Br minus. Now, what is the difference between those two? Okay. Already in the discussions that we've had today, Br minus we've addressed is a halide, which makes it a nucleophile. Nucleophiles push substitution. I don't want a substitution reaction. I actually want the elimination, which means having a nucleophile is a bad idea, which means bromide is a bad answer choice. Well, doesn't the other one also supply a negative? Wouldn't that act as a nucleophile also? Favorite 9-letter word. The resonance stabilization of that structure makes the sulfate ion non-nucleophilic. So it becomes a fantastic acid to use when all I want is an acid. If I need a nucleophile, now I can also switch into my halides and I can use HCl, HBr, HI. But if all I want is an acid, H2SO4 is going to do it for me. Okay? And very little else will. So the answer in this case is actually B. Okay? Pretty much the complete opposite of where our whole discussion started and went. Yay!
Could you give a quick definition of protonated and deprotonated?
Definition of protonated versus deprotonated?
Yeah, because I really haven't heard you say it that much besides in the recent videos and exactly.
Let's try it this way. So in red we have hydroxide. If we protonate the hydroxide, we are putting a proton on it. There's our proton. So this would now be protonated hydroxide because we've added a proton to it. Okay, proton just being H+. If we wanted to deprotonate hydroxide, we would then have to remove. So deprotonate, protonate, would mean removing that hydrogen. What would it look like if I got rid of that hydrogen? Well, now I would just have hydroxide. Does that make sense?
Yeah.
So protonated versus deprotonated typically happens more often when looking at amino acids, and we refer to the protonated state versus the deprotonated state. When we're looking at these kind of reactions, we'll talk about protonating something to make it a good leaving group. Really all we're doing is saying we're running an acid-base reaction. Where the hell are we? 26? Is this 26? Hopefully we're okay with that one now. I see a 19. Did we do? No, we didn't do 19. Oh, most likely to occur in acidic solution. So, first thing I'd want you to kind of trigger on would be that word acidic. Fine. Nope, not fine. God. It's awful. Oh, it just doesn't want to do anything I want it to do. Okay, well, recording's gonna suck. So, oh wow, it really sucks. So that word that's not showing up over there is acidic solution. So if we're in an acidic solution, what would we expect to see floating around? Well, we'd expect acids. And what do acids give us? Acids give us H+. Okay. So we could be looking for systems that have a bunch of H+ floating around, and that could be a good symbol. Okay. The other thing that's going to be useful to associate for us is not just the presence of H+, but the lack of OH-, and more importantly, the lack of strong bases. Okay? If we see a strong base, well, how did a strong base form if we're in an acidic environment? That just doesn't make physical sense. Okay, so we want to be looking for positive charges, and we don't want to see negative charges. Okay, so let's pull back out of this, take a look through our reaction. In this very first step, oh man, and can I draw? I can sort of draw over this. We'll just look at it weirdly. In this very first step, we're having the electrons attack, electrons there. So that on its face doesn't necessarily look bad. I don't see an abundance of negatives. I don't see an abundance of positives. One of the things that is a bit misleading here, though, is we have to make sure that the product of this reaction makes sense too. Then the product wasn't shown for us. If we go through and show the product, what do we end up seeing? Well, I would see H3O+. Well, that's not a big deal. What else do I see? A negative oxygen. Okay, that doesn't make sense. Okay, for multiple reasons now. I'm in an acidic environment, so I shouldn't see the negative charge. This reaction, in the process of it occurring, produces both a strong acid and a strong base. Just the mechanism on its own is actually an incredibly bad thing to do. We're forming exceptionally reactive species that literally contradict each other. So A is not a pleasant option. If we go through and look at B, what's happening in B? Okay, well, these electrons now come out, react with that hydrogen. Again, that arrow makes sense, goes to there. Okay, that makes sense. If we draw out the result, there's an oxygen, there's that hydrogen. Again, positive. That looks good. Not a big issue. What happened to the other part? We'd be forming a strong base. The formation of that strong base is, again, a bad thing to be happening in this system. So what we would then need to do is scroll down and look at the other answers, which maybe I can draw through. We've got this NH. We've got electrons from the electrons from a hydrogen going towards, this one's just bad because that curved arrow is actually nonsense. And if we go through and look at D, what's happening? Well, one good tip off is we see a positive floating around. That makes sense if we're in a strongly acidic environment. The electrons would flow towards that positive, so that arrow makes sense, but then I'd have hydrogen floating around on its own, so the nitrogen donates its electrons. Okay, those arrows look reasonable. If we draw out the results, nitrogen, we'd be forming a positive charge, also valid, and in this case we end up not forming a negative, we would just have a neutral oxygen. That's also okay. So the best answer out of all those choices is D. It's the only one that does not form a strong base in the environment, and it also shows the presence of acidic species through the course of that mechanism. So 19 actually makes the most sense, or D for 19 makes the most sense out of all of those. Okay? Cool. 29. Oh, frustrating. Okay, what do we think? Be like, easy, we don't even have to evaluate any structures, right? How hard can it be? High concentration of bromide. Well, there is a structure there, actually. We've got Br minus. Br minus. What does that minus mean to you? Hopefully what it means is that you have a strong, because it is negative, whoa, you have a strong nucleophile, okay? Which reaction would favor a strong nucleophile? Well, strong is a tip-off that we're looking at the two-type mechanisms, which means SN1 goes away and E1 goes away. Because it is a nucleophile, we should be looking for a substitution reaction, not an elimination. So D goes away. We're left with only one answer choice. B, SN2. Hopefully that makes sense. That was really fast. But hopefully that made sense.
With your buy also 28.
Yes, but I just want to check a couple things. Okay, I'm actually going to hold you for just a second. Victor and Anthony are still both there. Do you guys have questions? You've kind of just been riding silent for a little bit.
I'm trying to run through this slide 9 right now.
Okay, do you have questions with that?
I don't understand what I don't know. That's where I'm at. I need a minute.
Okay, that's fine. I just want to check, make sure you guys had an opportunity to chime in. And Victor? Okay. Dang it. Branson, you did an audible. Was it 28?
Yeah. Just clarification on this.
So, mostly stable. So if we're looking at mostly stable, we're looking at, we could be looking at the rules that I told you to track as far as, what are all those words? Charge, size, electronegativity, resonance, all that kind of fun jazz. And technically you would be using those to evaluate this, but where it's going to end up going down to is into that kind of oh crap catch-all category, and it's going to be a substitution. So what we'd be doing, is looking at these structures and trying to find what is most reactive in each of them. The most reactive thing in each of them is the pi bond. So, and the reason it's most reactive is the pi bond is made up of p orbitals. Those p orbitals are higher in energy than the sp3 hybridized orbitals for all the other bonds. Okay, so our p orbitals are our most active. We now need to evaluate their stability. We could try and look for resonance to see if there was some kind of resonance argument that we could use, but there's no resonance here, which really means we're left with looking at substitutions. So in that substitution pattern, what we're evaluating is what things are connected to the pi bond. This can be confusing. I get people misusing it all the time. Okay? Because people would be like, oh, they're all doubly substituted because they each have 2 carbons. You've only referenced the atoms of the pi bond. What we're looking at is the atoms or the things connected to the atoms of the pi bond. Okay? All pi bonds or all alkenes, not just pi bonds, so all alkenes have 4 things connected to them, always. Okay, so when we're considering stability, what we're considering is what would be different about those things. So what is the minimum that could be connected? The minimum connected would be hydrogens. Okay, so when we're referencing stability, what we're saying is what things are not hydrogen and how do they affect the stability of the pi bond. Okay? Stability has to do with reactivity, which means those electrons have to leave the structure. For them to leave the structure, they must venture forth outside of it. Okay? If we look at this as kind of a flat structure, which is not officially true, and this is kind of a hand-wavy argument, but it works well. If we look at that first drawing, the electrons could leave the structure in 4 directions. They could go out this way, they could go out this way, they could go out this way, or that way. So 1, 2, 3, and 4. What would prevent the electrons from leaving any one of those directions?
Another molecule or atom.
Another atom. Why another atom? What does that other atom supply?
Electrons.
Electrons. So if we take a look at the map for answer choice A, 1 and 2, directions 1 and 2 are carbon atoms, whereas 3 and 4 are hydrogens. 1 and 2 with carbon atoms have more electrons. That creates kind of a steric repulsion, which means as the electrons come out, they will turn tail and go back in, which effectively nullifies their reactivity. Okay? So if we look at it, A really only has 2 options that are valid, or 2 good options. Okay? We could switch this up and refer to it based off of the carbons, because that's typically how we do it, and we could refer to this as di-substituted. That di-substitution is referring to those 2 carbons. If we go through and look at B, we're going to run the same kind of analysis, except B, instead of being di-substituted, is tetra-substituted. So all 4 potential sites are substituted with carbons. If we move to C, it is tri-substituted. Okay? Remember, the more substitution, the harder it is for the electrons to get out of the structure. Okay? So tetra-substituted ends up being the most stable. Di-substituted ends up being the least stable. Okay? So we should move, in this case, B, C, A. Does that give anybody flashbacks?
Yeah, that was a quick, we went over this very quickly on the video, so that's why I forgot about it.
No, I was actually referencing the B, C, A as a flashback, little PTSD, but that's okay. If you didn't get it, you didn't get it. That's fine. But yeah, that's what we're looking at there. There are cases where you have 2 di-substituted, like cis versus trans. Those are both going to be di-substituted. Which one's more stable? Trans gets those groups as far away from each other as possible. So the di-substituted category technically has 3 cases. You have cis versus trans, and then you have, I'm going to call it terminal, which is now the pi bond at the end of a chain. The more external the pi bond, the more likely it is to react. Or the less stable, I should say, it is. Okay. More questions? So with that lab, you've got to decide what you want. Okay, so if we go through and look at our procedure, what we end with is that we collect each substance, we get a weight, and we obtain a melting point. Okay? Weights in and of themselves are not results, they're data. Okay? So you need to convert the data into a result. That would be a percent recovery. Okay? So what percent recovery do you want for each substance? Okay? And that is entirely up to you. Okay? You could decide that they were equal, you could decide that they were higher, lower, anything. What you would have to do in the discussion is once you've made that decision, so let's just say you get a 50% recovery of the acid, a 50% recovery of the base, and a 50% recovery of the neutral compound. Okay? How did you calculate those percent recoveries? Okay? Because if I add those all up, isn't that 150% recovery? So you need to address how you're running that calculation to make sure that it actually makes sense. Once you've got those numbers, you can then evaluate the questions down here. Okay? So if it was 50% of the entire sample, if you were saying 50% of your sample was A, 50% was B, 50% was C, that should cause problems. Can you make conclusions about the purity of the unknowns? Well, just based off of those results, you're saying you got 150% of the stuff back. That's not physically possible, which means you can draw conclusions about the purity. The conclusion that you would be drawing is that they are all vastly impure and that you have somehow screwed something up through the process of that experiment. Okay? If instead you said 33%, 33%, 33%, could you now draw conclusions about purity? Well, that would total to be 100%. It's not over 100, so that doesn't mean that it is impure, but does that mean it's pure? When you get that yield, what's the guarantee that it was a pure substance? Okay? Does that number, 33% yield, guarantee that it's pure? Does percent yields do anything with identifying purity? It does identify impurity. Does it guarantee purity? Okay? Once you have that as a result, you can now discuss that percent recovery part of the experiment. Okay? This is broken into two parts because we get the percent recovery of each compound, and then we get a total percent recovery. A lot of this is addressing how you calculate it. If you assumed that it was a 1-to-1 mixture, then the most you could have gotten for each compound would have been a 33%. But a 33% would really be 100% recovery of that compound. I don't know that that made sense. Are you making faces at me because you have no clue what I just said? Okay, I needed to hear that or see that. So let me try and draw this. I should have just erased everything. Oh, well. So you start with a mixture. A, B, ooh, sneeze. Oh, that sucks. C, right? So those all look roughly equal, right? That's the goal here. So let's take a look at how we calculate percent recovery, and this becomes the important part, okay? So here's A, here's our B, and then I am attempting to color code this for the calculation because it's kind of important. So we have 4 colors being associated here. We have a color for each compound, and then we have the black as our color for everything. So if I decide to calculate the percent recovery of A as the actual, or let's do it this way, experimental A that we obtained, but I divide that now by the total, the black thing, okay? If we look at my approximation of those boxes, these are supposed to be roughly a third each. I'm going to try and avoid percentages, but a third of each. Okay. What would my percent of A be? Okay. Well, if I'm looking at the entire total, that would be 33%. Okay. But if I look at this instead as my experimental of A over the theoretical, okay, that could get reported up to 100%. Okay, that theoretical is this entire A section. This black was the entire total. Depending on which way I'm running my calculation, that's going to change the number that I output, which is going to change my interpretation. So you have to be careful that you explain that process of what you're going through and looking at. So if you go through and tell me you got a 33% yield of A by running that top calculation, what I'm calling the black one, okay, that I should expect a 33%. You're now saying it's 1-to-1 for all of them. If you instead tell me that it's 100% of A, okay, well now I'm assuming you're running this based off of the theoretical maximum you could have obtained. But if you're telling me you got 100% based off of a black calculation, you're saying you ended up with 3 times the amount you started with. Does it make a little more sense? Okay. So, your next statement is then what are your possible ranges that you could have had? Okay. So you could have said that it was a 1-to-1 mixture of everything else, but you didn't obtain all of that mixture. That's okay. Okay. And so in that approach, what I would argue you should be doing is kind of reporting your percent recovery, okay, of A according to that theoretical maximum. Okay. So we're not going to pick an easier number because that's what I gave you. 200 divided by 3. Calculator. So you were saying, yeah, of course, you smart aleck, that your theoretical maximum was 66.6 technically milligrams of compound. Okay, that was your maximum. And so you're saying you obtained something less than that. Let's just say 50. Okay, this is your kind of report out. So what you would then tell me is 50 divided by 66.6 that you 0.6 that you got a 75% recovery of A. If you went through and assumed that that result was the same for each of those substances, at the very end, your total percent yield would now be 50 for A, plus 50 for B, plus 50 for C. Out of your total 200 possible, you would get 150 out of 200, which if it was the exact same is going to come in at 75% yield. That number, that red number, really sucks not being able to point to things, obviously. That number there, this is what you get to determine. But you're going to determine it for A, B, and C, for all 3 compounds. Okay? And you get to decide what that is. You use that result to come to that data to come to a result. That result is the percent recovery, okay, for each compound. Okay. I don't want to delete everything. Maybe, nope, I'm not going to delete everything because I do want to see the text underneath or point to that. But what we just addressed there is what I would argue is part A of the percent recovery analysis. What is your percent recovery that you got for each compound? It doesn't make sense to do that calculation out of the total because the total wasn't all compound A. Okay, so you should be giving me 3 values. Okay, 3 percentages like this: 1 for A, 1 for B, and 1 for C. Okay, that's part A of the percent recovery. Part B of the percent recovery is now recognize what your total recovery was. Okay, that part B is this bottom part here. This is now part B. Okay, if those were the numbers you picked, what was your total percent recovery of this? So, and Sierra, I see where your question is, and we have to be a little bit careful with that. Dividing by 66.7 means you are now following exactly what you know somebody else is already doing. Because Danielle's saying, I'm going to say it's 1 to 1 to 1. Okay? You are now copying that result, which could potentially be a bit shaky. Okay? It could not be also, because you also get the freedom to adjust with what you've decided that determining number is. Okay? But just realize where you're on a little bit shaky ground. So there's 2% recoveries to calculate. There's one that's what was the total part available to it, and there's one what was the total for everything. Okay, so I would argue to Sierra's question, so should we be dividing by 66.7 or can we do it by 200? You do it both ways. You do it 1 to represent the yield for each compound, and then you do it by 200 to represent your total collection back. Robert, yes. Does that make sense, guys? So Sierra, to your question, no, I don't think you should be doing that. Okay, dividing each number by the total doesn't really make sense, because by dividing by that total, you're saying in that total, it could have been A, or it could have been B, or it could have been C, an individual. You're dividing by a different unit system that doesn't really make sense to divide by at that point. But you're now saying that this part made up this aspect of the total when what you're trying to do is address how much did you recover out of it. It's not necessarily wrong, but I think what you'll end up doing is confusing yourself with how you have to discuss each result. And so that's why I would say no to the calculation that you're trying to do, is dividing them all by the 200. And then Danielle, do you feel more, less? Where are you figuring it out? I like the confidence. So are we okay-ish with the lab stuff? And I can't remember if I actually said it with the lab stuff. The due dates are there to kind of move you through the labs with what is hopefully enough time to complete them, i.e. 1 week before the end of the semester. The due dates are pretty soft, so don't stress about those. I do need to go in and check the quizzes, because I think the quizzes are open, that you could take them at any point, but they have due dates associated with them. But I think they're open availability. Oof. I did hear you. Give me a sec. So to Robert's question about question 30, what does it come out to be? It's not an easy question. It's actually probably, in my opinion, one of the hardest questions that you will see. And you will see questions like this. Question. They don't always come out to be this difficult, but it's challenging. And yes, you can always send calculations to me. So for multiple choice 30, it says an E2 reaction. The complication that you need to know for an E2 is that it has to be anti-periplanar to do the alignment. So the leaving group and the hydrogen need to be aimed opposite directions. If we take a look at how this drawing is set up, they are not aimed opposite directions or completely opposite directions, which means we would have to do a rotation. I'm going to leave the bromine side alone, and I'm going to rotate the other side. I need the hydrogen down here. So I'm rotating about this bond. As I do that rotation, the methyl will now be aimed up, the ethyl will be aimed back, the methyl will be aimed at me, the ethyl will be aimed away. Okay, that now aligns the hydrogen with the bromine in the proper configuration to do the elimination. Okay, which means we'll now run the elimination and we'll be forming the pi bond in here by getting rid of these guys. Because it is all happening at the exact same instant, I shouldn't have shown that permanently aligned like that. At that same instant, the stereochemistry gets locked into place. So CH3 wedged, phenyl dashed, ethyl dashed, which is the same as just kind of turning this now on edge. And we should get phenyl, ethyl, CH3, CH3. To Robert's question of it being cis, ethyl is a higher priority than the CH3. Whoops. So we should star the ethyl. The phenyl is a higher priority than the CH3, so we should star that. And those would be located on the same side, and we would get the cis product. Okay. I'm a little bit hesitant to throw this kind of cheat at you, but if you see a reaction drawn this way, and you know you're doing an elimination, particularly if it's shown as an E2, if you are running low on time, pick the cis product. And the reason for that is that most people will jump to the trans product because the trans is more stable. If the reflex is to draw the trans because it's a more stable, the design intent behind the question should be to make those people suffer and get it wrong because they didn't understand the chemistry that it needed to be the proper alignment. Okay, be careful with that. This is one of those. I know that you know that you know that I know what I'm writing situations. So, or Princess Bride with the poison thing. So be a little bit careful with those. But if you're short on time and you're seeing an E2, make it cis. Definitely not a guarantee. But your odds are probably better than the 20% guess on it. Okay, you're probably getting more into that 30-40%. Okay. Thank you. I thought that was a good reference myself. Then yes, Anthony, when I got a sec, what am I looking at?
So for part A, question 1, am I in the right ballpark by calling that 0.021 moles of copper?
Oh, Jim, I don't know the freaking answers. way to be specific. God. It's a low number, so in that ballpark, that makes sense. What are we doing? A minus D. 2 point. What did you get? 0.002?
0.021.
I think you need another 0. Because the mass of copper you got was what, 0.13?
Mass of copper metal that reacted is 0.1303.
And then to get the moles of copper wire that reacted, so that's grams. How do you convert grams to moles? You would need moles over grams, periodic table, which I'm going based off of what I vaguely remember. The molar mass for copper is 63.5. And I can't find that easily. Of course. Hey, look at that, 63.5. So yeah, 0.13 divided by 63.5 should be 0.002.
Roger.
You might have just misentered something. Because yeah, you're off by a factor of 10. So I would think you either added a decimal point. I think I would bet your work looks good, but you did something wrong in the calculator.
I think I missed entering because I'll have to go back to the calculator. But I think I just missed one of the zeros and then put a 1 there because of sig figs.
That could do it.
And the next one should be 0039. I just need to see if I understand.
Yeah, no, I'm.
Just go do the rest. It should be 4 because it's
0039, yeah. And yeah, you should watch out for the for sig figs. I think you should be getting 0.003901. The 2 zeros out front aren't significant. Did you catch that? Okay. Robert, SN1, because leading group is tertiary. So a tertiary location, tertiary substrates, SN1, fantastic reference. Is that nucleophile a weak nucleophile? Yeah, with it being strong pushes the 2-type reaction. Well, but it shouldn't be SN2 because that's a tertiary substrate. But E2, tertiary substrates, very good. Because you'd form a more substituted double bond. So you're actually going to get the E2 elimination in this. You're not going to get the SN1. That strong base is actually going to deprotonate. Remember, the nucleophile needs to be small, but a small negative can still act as a base. So with that sterically hindered substrate, that is not going to get in to act as a nucleophile easily, and what you'll end up getting is the elimination. And unfortunately, I just saw the time, guys. So I need to kind of be getting out of here so I can try and get some work done and pick my son back up from daycare, who screamed and cried all morning. So yay. So I will still be checking email. Officially, I am not checking email. So if you get weird comments, like for the 1:30 practice exam, seeing comments from phantoms or seeing phantoms responding to emails or weird bracket stuff, that's me attempting to say that I'm not working. But I am responding to email. I am checking things. If you send me messages through Canvas, which a bunch of people have done, it is significantly more difficult for me to respond through Canvas. And significantly easier to track that I'm doing stuff that I shouldn't be doing. So I do not recommend you sending stuff through Canvas. The more you can put in your email as far as images or text where you're having problems, the better. Because where a lot of my responding to emails is coming from is from my phone. So if you're saying you're having a hard time with question 4 in the homework, you're now asking me to pull up question 4 and have an email response, and that's less likely to happen from my phone. So it'll get pushed to later in the sequence. I still will get to it officially on Friday, next Friday. But that may be a bit late considering your exam 3 is this coming week. So I will be responding, but you got to give me a little bit more time to do that response. Okay? Any last second questions? Logistics? Okay, it's looking like everybody's okay. Again, I will be trying to check the practice exam files, those shared documents, for comments and try and provide feedback as I see it. We did just talk through a whole bunch of these, and it is in a literally 80-minute video. Nope, that's a lie, because I think it actually goes up to 100. So it's in 120 minutes worth of video, which will probably take my internet forever to upload, but I will get that uploaded as soon as I can.